Hi people, hope we're doing well. We're going to discuss two more varieties of indeterminate forms of a limit. The first one we're going to deal with is indeterminate difference. Okay, so anytime you have something which gives you infinity minus infinity, that is another indeterminate form. Now, basically, if we're given the limit as x approaches 1 of 1 over natural log x minus x over natural log x. Now this one's going to reconcile really easily, but we know that basically when you plug in 1 into here, it's going to make these two ratios the same, right? It's going to be 1 over natural log of 1. Well, natural log of 1 is 0, okay? So as the denominator is approaching 0, you have 1 over approaching 0 minus 1 over approaching 0. So you have infinity minus infinity. The question is, how does it all work out? Okay. Well, this one, since it already has the same denominator, it winds up being really, really easy. You just smush them together, right? And of course, once you smush them together and you have this ratio of 1 minus x over natural log x, you still have it in indeterminate form. It's just one of the indeterminate ratio forms. It's 0 over 0. So basically from here we take L'Hopital's rule. That's what happens in this one. And the derivative of 1 minus x is negative 1. The derivative of natural log x is 1 over x. And therefore when we simplify, it just becomes negative x. Well, limit as x approaches 1 of negative x is obviously negative 1. And that one's actually relatively easy. Now this one right here, the limit as, this is going to be a little bit more difficult because we're going to have to get a common denominator in order to turn this into a ratio. But let's make sure that it's indeterminate first. 1 over 0, 1 over x, and that's going to of course be infinity, and we'll assume that it's coming from the right. Now the limit as 1 over e to the x minus 1, that's going to approach 1 over 1 minus 1. So that's also going to be infinity. So it's going to be infinity minus infinity, and so we have to basically turn it into a single ratio and use L'Hopital's rule. Now, since both denominators are relatively prime, meaning that they don't share any factors, I need to multiply this ratio by this denominator over itself, and this ratio by this denominator over itself. Okay. And what happens, and I'll go ahead and show that step, that's fine. E to the x minus 1 over e to the x minus 1 times 1 over x minus e to the x minus 1 times x over x. Okay? And then when that simplifies, you're going to have the same denominator. You're going to get the limit as x approaches 0 from the right. And we get e to the x minus 1 minus x, all of that over x, e to the x minus 1. Now let's go ahead and check. This is still an indeterminate because it's going to be 1 minus 0, or 0. And this is going to be 0 times 0. So it's still 0 over 0, still an indeterminate form. We have not yet, however, done L'Hopital's rule. We have merely changed the form so that we can. So let's go ahead and do L'Hopital's rule. The derivative of the numerator, just term by term, so e to the x minus 0 minus 1. Okay, and then in the denominator, it's going to be the product rule. So the first times the derivative of the second plus the derivative of the first times the second, and yay, there we go. Now, that was L'Hopital's rule to get to there. This next step is simply going to be cleaning it up so that I know what I'm dealing with at this point, okay? And what I have here is I have x, e to the x, plus e to the x, minus 1. Okay, well let's plug in and see whether we need L'Hopital's rule again. The numerator is going to be 0 minus 0. Yeah, that's not looking good. This term, because one of the factors is 0, it's going to be 0 plus 1 minus 1. So yeah, you're still going to get 0 over 0, so we have to do it again. Now, what we're going to do here is the limit as x approaches 0 from the right. The numerator is getting a whole lot simpler, right? The denominator basically what happens here is you're going to have x times e to the x, and that's going to be, we've got to do the product rule again, right? So x e to the x plus e to the x plus e to the x minus 0, right? And the quotient rule is these two terms. And so we need to do another round of simplification. And so we have e to the x over x e to the x plus 2 e to the x. Well, you know what? All of a sudden I'm realizing that there is now a common factor in the numerator and denominator. Boom, boom. And I don't have to use L'Hopital's anymore, because all of a sudden I have something that is capable of being evaluated. And I'm done. Okay, so indeterminate difference, the method or the logic behind it is the same as when we had an indeterminate product, and that is, if it's not a quotient, turn it into a quotient. Okay, so let's go ahead and let's move on to the last three. And the last three are all kind of grouped together as indeterminate powers. Okay, if you get 0 to the 0, if you get infinity to the 0, if you get 1 to the infinity, all three of those are indeterminate powers, okay? And they need to basically be changed in form. Now, this one is a little bit more complex because oftentimes it basically has something like this, okay? And we know that the problem is we have an exponent, we have a variable in the exponent. And that's never good, okay? A variable in the exponent is something that we don't really like, we have a hard time dealing with, and of course, we have a way of dealing with it. And that way of dealing with it, the way of yanking down, basically the way of pulling down variables out of the exponent, we use natural logs, okay? So basically this is a limit, you know, the limit as x approaches 0 from the right of some function that we'll call y. And y is, of course, this expression. Well, if we define that as y, what we need to do is we need to take the natural log, and that allows us to pull down that 3x. Now, of course, from here, you can actually do a little bit of simplification if you want, okay? And by simplification, I mean this, okay? You can take natural log y is equal to 3x natural log 2x, and you can basically split that up. That becomes 3x times natural log 2 plus natural log x if you want to. You don't have to. And basically that then becomes 3 natural log 2 x plus 3x natural log x. I don't recommend doing that. It's not going to be all that efficient, especially considering the fact that you're going to have to take that natural log y, and we're going to be taking the limit of that natural log y. Now here's the thing. We can't take this limit of this as is. So what we're going to do is we're going to find this limit indirectly by basically evaluating not it, but a related limit. So let's go ahead and evaluate the limit of this, okay, which is of course our natural log y, and see whether that helps us to sort of back into an evaluation of the limit of y, the limit as x approaches 0 of y. Now, what I need to do is, again, I need to go ahead and turn what is not previously a ratio into a ratio. Well, the easiest thing to reciprocalize and stick down in the denominator is, of course, the x. Now, you can put it down there as 1 over x, or you can put it down there as x to the negative 1. Probably a little more efficient to do it as x to the negative 1. And so now I have this in terms of a limit, in terms of a ratio. And I know that the limit as x approaches 0, this numerator goes to negative infinity, this denominator goes to positive infinity, and so you have infinity over infinity. Once you've transformed it into a ratio, you still have an indeterminate form. And basically what's going to happen is I'm now going to take L'Hopital's. I'm going to use L'Hopital's rule and take the derivative of this. Now the derivative of natural log 2x is going to be 2 over 2x. So you just get 3 over x. And that sort of makes sense out of the fact that you could have simplified and pulled this apart into just a natural log x, right? So what we need here is basically just 3 over x. The 3 comes along for the ride. The 2 over 2x simplifies into 1 over x, and they combine into 3 over x. This is x to the negative 1, which becomes negative x to the negative 2, or negative 1 over x squared. I now have a complex fraction. When I seek to simplify the complex fraction, I simply get the limit as x approaches 0 from the right of negative 3x. Well, that's capable of being evaluated. I plug in, and I get 0. So here's the logic. If the limit of natural log y goes to 0, then the limit of y, because it can be rewritten like this, y can be unsimplified into e raised to the natural log y. If this piece, basically, if this piece right here is going to 0, then that whole expression is going to e to the 0. And e to the 0, as we know, is simply 1. All right, let's go ahead and do more examples. Yay. All right. Now, this, obviously, ugly. Let's go ahead and plug it in. This is going to be 1 minus infinity, right? So 1 minus infinity to the 0, so it's negative infinity to the 0. That is one of our indeterminate forms, okay? So we need to go ahead and recognize the fact that y is equal to 1 minus 1 over x to the x. And that means that natural log y is equal to x natural log, and you can put this as 1 minus x to the negative 1 if you want. That makes it a little more manageable in terms of sort of notation. Or you can just leave it as 1 minus 1 over x. It doesn't really matter. Now we're going to take the limit of this as x approaches 0. And that is going to allow us, just like the previous example, to sort of back into the limit of this. All right, so let's go ahead and formulate that. We have the limit as x approaches 0. Now, remember that I need it in terms of a ratio. So the easiest part of this to actually shove down into the denominator is, of course, the x. So what we have here is we have the natural log of 1 minus 1 over x over 1 over x. Or you could do either to the negative 1. It doesn't really matter. But when you look at 1 over x, you're automatically thinking x to the negative 1, so I wouldn't really worry about it. Now, from here, I need to use L'Hopital's. So in the numerator, remember that anytime it's natural log u, it's 1 over u times u prime. So this is actually going to get kind of disgusting. And so what I have is the derivative of the argument is 1 over x squared, and then it's just 1 minus 1 over x. And of course down here, this is negative 1 over x squared. Isn't that pretty? And the answer, of course, is no. What I need to do now is I need to resolve the complex fraction. Okay? And when I resolve the complex fraction, it's going to, this is basically a step in simplification. I have 1 over x squared, 1 minus 1 over x, and instead of dividing by this fraction, I'm going to multiply by its reciprocal. And that's going to give me the limit, and this is still simplification, negative 1 over 1 minus 1 over x. Now, again, it's still a complex fraction. Let's go ahead and simplify again by multiplying by x over x. We have the limit as x approaches 0 of negative x, and then x minus 1. Well, I tell you what, all it took was one round of L'Hopital's and several rounds of simplification to get it into something that I could recognize as a limit that was capable of being evaluated by plugging in. I plug in, I get 0 over 0 minus 1, and that, my friends, is 0. Now, what that means is that the limit as x approaches 0 of y is the limit as x approaches 0 of e to the natural log y. Well, this is the limit of natural log y, so if that little piece goes to 0, then this whole thing goes to e to the 0, and that is just 1. Yeah, and oftentimes they go to 0 and it becomes e to the 0 and it goes to 1, but sometimes we're lucky and it's not so boring. But let's go ahead and do another example. Now, this is y, x to the 1 over x. Again, I'm going to take the natural log, and thankfully this basically becomes already a ratio, so I really don't even have to do much work to turn it into a ratio because it just is one. Now that I've transformed y into natural log y, I'm going to go about the work of determining the limit of that related limit and allow that to help us indirectly find the limit of the original. Now this of course is going to be infinity over infinity, but when we take L'Hopital's, when we apply L'Hopital's, we get 1 over x over 1, and therefore this just becomes the limit as x approaches infinity of 1 over x, and that is 0. Okay, well if the limit of natural log y is 0, the limit as x approaches infinity of y, we know that that is the limit as x approaches infinity of e to the natural log y, and if as x goes to infinity, natural log y goes to 0, then e to the natural log y goes to e to the 0, and again, we get that wonderfully boring answer of 1. I really got to go searching for problems of this variety that have answers that are a little bit more fun than that. Basically, I think the reason is if they're too complex, then they wind up being just too burdensome. I mean, it's already a burden to have to change y into natural log y, find its limits, and then apply it back to the original limit. And so I think a lot of the worksheets and the textbooks that are out there, they basically don't want to overly burden the student with even more layers of complexity, so the answers to these wind up being wonderfully mundane. But let's go ahead and let's do y is equal to cosine x to the 1 over x. Again, bring down that exponent when we take the natural log of both sides, and of course that's the natural log of cosine x over x. It already is a ratio, yay us. So we have the limit as x approaches 0 of natural log cosine x over x. Now, the limit as x approaches 0, if I plug in, right, I'm going to get natural log of cosine 0, or natural log of 1. Natural log of 1 is 0, and so if I try to plug in and evaluate it, I'm going to get 0 over 0. So, and that should happen, right? When I change the form, it should still be indeterminate. Or when I basically figure out the related limit, that related limit should still be indeterminate. And so let's go ahead and apply L'Hopital's. And I know that when I take the derivative of natural log of anything, the argument of the logarithm goes in the denominator, right? So cosine goes into the denominator. Its derivative goes into the numerator, which is negative sine, and of course that just becomes negative tangent. And the denominator, its derivative, is just 1. Well, I don't care about the negative, but tangent of 0 is just 0, right? So again, we have the limit as x approaches 0 of y is equal to the limit as x approaches 0 of e to the natural log y, and that becomes e to the 0 or 1. Okay? Now, that's several examples. They all kind of wound up being the same answer, but of course the working out of them were different because the functions were different. We'll do more of these in class, but if you have any questions, as always, please do shoot me an email. Bye.